I wanted to mention a couple other things about this nematic order tensor, the Q tensor, um, and then go on to begin talking about the isotropic nematic transition today. As you recall, we have defined this nematic order tensor, a tensor order parameter for the nematic phase, and could write it as some Qij, which is the average of this quantity, 3/2 L alpha L beta minus a half delta alpha beta. Whoops, my indices don't match. Okay, well, I'll call it Q alpha beta. Okay, Q alpha beta, much better. Now, so this is the average that we came up with, where L is a orientation of the individual molecule. Of a molecule. And so we are averaging this combination of molecular orientations. And what we get from doing this average is a tensor order parameter, which can be interpreted as a scalar S times a combination 3/2 N alpha N beta minus a half delta alpha beta, where this describes the orientation of the nematic phase, and this S is the average of the P2 of cosine theta. That is the average of 3/2 cosine squared theta minus a half. And this represents the quality of nematic order, the magnitude of nematic order. And so it would distinguish whether we're in a nematic phase or an isotropic phase. So in the homework number 6, which is now posted on Blackboard and is due in a week, you'll have the opportunity to practice with some simulation data. So I'm giving you an example of some simulation data where you can see the orientation of about 1,000 molecules. And then you can calculate what is the Q tensor and determine whether a phase has nematic order or not. Now, to mention a couple of mathematical properties of the Q tensor, these are sort of standard things that people often talk about. One is that, not problems, properties. One is that the tensor is symmetric. That is to say that Q alpha beta is equal to Q beta alpha, right? So symmetric means symmetric under exchange of the two indices in the tensor. And another property is that it is traceless. That is to say, the trace of Q is equal to 0. And it is that way by construction, right? The trace corresponds to what's happening in the isotropic phase, and we intentionally subtracted off what's happening in the isotropic phase so that we could distinguish between nematic versus isotropic. Excuse me. One way we could check this is to calculate the trace explicitly. Okay, so if we wanted to check it, right, the trace of Q, that's the sum of all the things on the diagonal. Okay, so it's QXX plus QYY plus QZZ. So we could write it as Q alpha alpha, right, which is automatically summed over alpha equals X, Y, and Z. So that is S times 3/2 N alpha minus 1/2 delta alpha alpha, like that. Okay. Now, N alpha alpha, that is N dot N. N is a unit vector, the director of the nematic phase. So N dot N is 1. Delta alpha alpha, well, that is delta XX plus delta YY plus delta ZZ, right? So it's 1 plus 1 plus 1. It's 3. That's the dimension of space, right? So this is S times 3/2 minus 3/2. So that is 0. Okay, good. Now, you could say, this Q tensor, it has a magnitude and a direction, right? The way we were speaking about with visualizing tensors, right? There's a magnitude and a direction, or you could say there are magnitudes and directions associated with the tensor, right? You remember when we were talking about how to visualize a tensor, step 1 was to break it into a symmetric part and an antisymmetric part. Well, here it's already symmetric. There is no antisymmetric part. Okay, so we can just visualize it the way we would visualize a symmetric tensor. Okay? So I argued for you before that the magnitudes of a tensor are the eigenvalues of the tensor. In this case, the eigenvalues are S minus 1/2 S and minus 1/2 S. Right? We know that because in the case where order is along the Z direction, we already figured out that the Q tensor is minus 1/2 S minus 1/2 S, S, right? 0, 0, 0, 0, 0, 0, right? And so this is a tensor which is diagonal, okay? And so the idea of eigenvalues, right, is that you want to put a tensor into diagonal form in some coordinate system, and then the eigenvalues are the elements along the diagonal. So here, it's already diagonal, and the elements along the diagonal are these 3 things, S minus 1/2 S and minus 1/2 S. Okay? So these are the 3 eigenvalues of the Q tensor. when order is along the z direction. But if it's true for order along the z direction, it's true for order along any direction, right? This is a statement that doesn't have to do with coordinate systems. So it's true in any coordinate system. Right? And then each eigenvalue corresponds to an eigenvector. Those are the directions associated with the Q tensor. So the eigenvalue S corresponds to the eigenvector N. Okay. The other two eigenvalues correspond to two unit vectors perpendicular to N. In the case where the two eigenvalues are degenerate, that is, these two are equal to each other, then you can take any combination of unit vectors perpendicular to N. It doesn't matter what combination you get. You take any of those things would be an eigenvector associated with this eigenvalue of -1/2 S. So this Q has one special magnitude and special direction, and the other two equivalent to each other. Right? So this tensor is something that you could visualize as an American football. Right? It is a tensor that could be visualized as an ellipsoid, which has a long axis along N. So here's N. Okay. It has a long axis along N and a short axis, which is the same this way or that way, right? Everything in the plane perpendicular to N is equivalent, right? So that's like an American football that's long one way, but it doesn't matter which way you go perpendicular to the long axis, it looks the same, right? It looks like a circle in the plane perpendicular to the long axis. The mathematical word for that is uniaxial. That is to say, there is one special axis and the other two axes are equivalent to each other. Okay, so it could be an ellipsoid that is oriented vertically like this, right? That's a liquid crystal which is aligned with the director along the z-axis, or it might be horizontal. So, an ellipsoid this way. This is not a very good looking ellipsoid. Let me try again to draw that one. Oops. Let me try again to make it a little bit more symmetrical looking. Something like that. Okay. All right. So it could be oriented vertically or horizontally or in any direction, diagonally. Right. But in any of these possibilities, right, N is the orientation along the axis. Right? And N is equivalent to -N, right? We could equally well draw this vector or this vector. It doesn't matter which we pick. Either of those things describes the same physical state of nematic order. So think back to when you were first learning about vectors, right? When you first took a physics class and you learned about vectors like a velocity vector, right? And so you know at that time, one way that you could represent vectors was by listing the x component, the y component, the z component. Right? Another way you could represent a vector was by describing the magnitude and the direction. Right? And so when you were first studying physics, right, you probably had problems where you say, oh, okay, well, suppose, a projectile is moving at 45 degrees up from vertical at 10 meters per second, right? What are the x and y and z components of the velocity vector, right? You did that sort of thing, right? And likewise, you had problems where somebody would give you what are the x and y components, 0.7, negative 0.3, right? They would give you the x and y and z components, and you would have to say, what is the magnitude of the velocity and what is the direction? Right? So the same thing works here, right? I could give you a problem where I tell you what is the magnitude S and what is the director N. And from those things, you go to the Q tensor. Right? And you figure that out by just it's S times 3/2 n alpha n beta minus a half delta alpha beta, right? So this would count as an easy final exam problem, right? To work out what are these 9 components of the Q tensor, right? And vice versa, you could have a problem where I give you the 9 components of the Q tensor, and you have to figure out S and N, right? And you would do that by calculating the eigenvalues and eigenvectors of the Q tensor. And this S would be the largest eigenvalue. It would be the only positive eigenvalue. And N would be the corresponding eigenvector. So, and you'll have to do something like that in the homework that I just assigned for you. Okay. I guess the last point that I want to make about the Q tensor in general has to do with counting the degrees of freedom. So let's think about how many degrees of freedom there ought to be, right? So we would say there's the magnitude S, that's 1, right? And then there's the director N, okay? The director N is a unit vector, right? Pointing somewhere in space, right? So to describe a unit vector, you need to say, what's the angle going down from vertical? And then what's the angle going around in the XY plane, right? What's usually called theta and phi. Okay, so the director n has 2 degrees of freedom. Okay? And that's normal for a unit vector. In general, a vector, an arbitrary vector in 3-dimensional space has 3 degrees of freedom. But when it's a unit vector, that's an extra constraint and it knocks it down to 2. So we think there should be 3 degrees of freedom. Okay? But another way to look at it is to say that, that we have a symmetric traceless tensor. Okay, so what can we say about a symmetric traceless tensor? Right. Well, how many elements do we have to choose? Right. Well, first of all, we can choose what goes on the diagonal. Okay, so there's some Q11, Q22. Okay, now what about in this position? Well, the tensor has to be traceless, right? The trace has to be 0. So the things on the diagonal have to add up to 0. So this better be negative Q11 minus Q22, so that these add up to 0. Then for the off diagonal terms, you have to choose Q12, Q13, Q23. But then what goes here has to be the same as what's there in order for the tensor to be symmetric. Likewise, whatever goes here has to match what's up here. Okay, so this has to be Q13. This has to be the same as Q12. This has to be Q23 in order for the tensor to be symmetric. Okay? So of these 9 elements, 4 of them are constrained by the constraints of being symmetric and traceless. But that still leaves 5 numbers that we have to choose. So it looks like there are 5 degrees of freedom. So if you compare these 2 counts, something looks wrong. Okay, these 2 counts don't agree with each other. Okay? The reason for the discrepancy is that this Q tensor formalism is actually more powerful than what we need here. It's more powerful than what we need for describing a uniaxial nematic phase. That is because the Q tensor can also describe biaxial nematic order. Biaxial order means the describing objects that are not shaped like an American football, that have a circular cross section. Okay, they describe objects that are shaped like a box. Okay, so suppose you have a box like this, where the 3 directions are all different from each other. Okay? There's a long direction, there's a medium direction, there's a short direction. Okay? In that situation, you need 2 angles to represent what orientation is the long direction, down from the vertical and going around. You also need a magnitude to say how long is the long direction. All right, that covers the uniaxial part, but that doesn't tell you about what's going on with rotations about the long axis. Okay, so you still would need 2 more numbers to represent what's the magnitude of the difference between medium and short, right? And what's the orientation of the medium direction in the plane perpendicular to the long direction. So those extra 2 degrees of freedom that are not accounted for describe the possibility of biaxial pneumatic order. Now, the concept of a biaxial pneumatic phase is a theoretical concept that a lot of people are interested in, but it's not a common thing experimentally. Okay. So there are speculations that there can be a biaxial pneumatic phase. I'll say by a biaxial pneumatic phase, question mark, right? Can there be a biaxial pneumatic phase? Well, if there were a biaxial pneumatic phase, right, it would be something where the tensor has a long axis, a medium axis, and a short axis. That is, medium and short would be different from each other. This is certainly a theoretical possibility. There has been a lot of experimental controversy about whether this has been found experimentally. Some people believe that they have found it in the lab. Other people believe that those experiments are mistaken, that there's a different interpretation for what's going on in those experiments. I'm not going to take a stand one way or the other on that point. It certainly is a theoretical possibility, and it could exist somewhere. But it is not the normal experimental phenomenon, right? The normal experimental phenomenon is a uniaxial pneumatic phase, which has a long axis and a short axis and another short axis. And these two are the same as each other. All right, so those are my general comments about the Q tensor. And look, I've taken up half an hour already with general comments about the Q tensor. Are there any questions about this kind of a subject so far? No, okay. Well, you can practice with the homework and see if you have questions as you go along. Okay, so now let's compare what we might think about for the phase transition, right? So let's think about the phase transition for isotropic to pneumatic, right? And I want to compare that with what we did at the beginning of the semester for the transition from a paramagnetic phase to a ferromagnetic phase. So with the isotropic pneumatic transition, right, we have a tensor order parameter, Q alpha beta, which has this interpretation of S times 3/2 and alpha beta minus a half delta alpha beta. Right? That corresponds in the magnetic transition to this order parameter M, which could be interpreted as a magnitude, the absolute value of M, times a direction, which is just plus or minus 1. Okay? In this case, right, the magnitude, as you recall, was a function of temperature. The direction is random. It's determined by just spontaneous symmetry breaking. Okay. The same is true for the isotropic nematic transition. Okay, that the magnitude of the order S is a function of temperature, and the direction is coming from spontaneous symmetry breaking. Okay. Now, when we were working on the Ising magnet, as you recall, we had a way to determine things about the temperature dependence, right? So we could make a plot back then of what is the magnitude as a function of temperature. And so this was a plot that looked like it's 0 above the phase transition, and then there's a transition, and then it increases as a square root law, like that. So the absolute value is going just up, right? So back, when we were studying it at the beginning of the semester, I plotted it as the M itself as a function of temperature, which could go both ways, there and there. But of course, the absolute value just looks like this. It just increases. Okay, so now I want to do something like that for the isotropic nematic transition. That is, I want to make a prediction for what is S as a function of temperature, right? To see, how does the nematic order change as a function of temperature? And in particular, I want to see how does it go from S equals 0 at high temperature to S not equal to 0 in the nematic phase. Right, so S equals 0 is the isotropic, S not equals 0 is the nematic phase. Okay, so how can we do it, right? How can we calculate this? Right. Well, in the magnetic case, you remember we had two theoretical approaches, right? So one theoretical approach was the microscopic mean field theory. That is, we had a model involving a lot of interacting spins, and we couldn't solve that model exactly, but with the mean field approximation, we could solve it approximately. And then we had a second approach, which was Landau theory. And in Landau theory, we pretend that we don't know that the world is made out of atoms and molecules and magnetic spins. We just think about the symmetry of order parameters. And we can say, what can the free energy be in terms of the magnetic order parameter? And based on that, surprisingly, we were able to figure out things about the phase transition. Now, the same types of theories apply for isotropic nematic transition also. Again, we have a choice between doing a microscopic theory or a microscopic theory or macroscopic symmetry-based theory. Okay? So there are what I'll call microscopic or molecular theories. And in particular, there are two varieties of microscopic or molecular theory that you should be aware of. One of these is Meyer-Zalpa theory, and the other Ansager theory, which apply to different kinds of systems with different interactions, as I will show you. Okay? Or, as an alternative, we could do a more macroscopic theory, just in terms of symmetry and order parameters. And so that is a variety of Landau theory. And when Landau theory is applied to nematic liquid crystals, people refer to it as Landau de Gennes theory. So after Pierre-Gilles de Gennes, who did so much of the foundations of liquid crystal physics and won a Nobel Prize for that. So these are three theoretical approaches that you should be aware of for this kind of issue. Okay? And I want to discuss all of the theoretical approaches now. When we were talking about the magnet, I did the microscopic theory first and the Landau theory later. Okay. Here, I want to reverse the order. Okay. I want to talk about Landau theory first, and then the two versions of microscopic or molecular theory, Meyer-Zalpa and Ansager, like that.
Excuse me, a question. Are
Please.
those two microscopic theories mean field theory or
I couldn't hear it. Say again.
Are those two microscopic theories also mean field theory?
Yes, they are also mean field theory. So they also have the approximations that are built into mean field theory. Right? So, I mean, there's no exact theory. This is not the kind of problem that we can solve exactly.
Okay.
So for people who don't want to make the approximation of mean field theory, they could also just do computational work, right? They could simulate a system of 1,000 molecules interacting, right? Or 10,000 or 100,000. They're probably not going to simulate 10 to the 23rd molecules interacting, but they can simulate a lot of molecules interacting and see what happens as they go to larger and larger systems. That's a different kind of approach, which has its own pros and cons.
are the results from those two microscopic theories consistent with the Landau theory? Landau
Yes.
de Gennes.
Yeah. Yes. Yes. Um, as far as the transition goes, not as far as low temperature behavior goes, and I'll get to that in just a few minutes.
Okay, thank you.
Okay. No, I won't. I'll get to that next week. Okay, so let me begin with talking about Landau de Gennes theory. Okay, so I want to begin by saying, suppose we don't know anything about molecules, right? That all we know about a liquid crystal is the Q tensor, right? We know that it might have some nematic order. There must be a free energy which depends on the Q tensor. But how does it depend on the Q tensor? That's what we want to try to figure out. Okay, so the question for Landau de Gennes theory, I'll write it as LDG. Landau de Gennes theory begins with how does the free energy depend on the Q tensor for a small Q tensor. So you ask, tensor is small. What does it mean for a tensor to be small? Well, all the magnitudes of it are small, right? All eigenvalues are small. Okay, so let's approach that with the same style as what we did for the Ising magnet. Okay? In the Ising magnet, the question was, how does the free energy depend on the magnetic order parameter for small magnetic order parameter? Okay? And our answer was, whatever it is, there must be a power series for it. Okay? So we'll assume the same thing here, right? Whatever the dependence is, we must have a power series to represent it, okay? And so let's construct a power series to represent the free energy in a way that is a smooth function that has all the right symmetries, right? We have our constraints of smoothness and symmetry. Okay, so let's say we want to figure out the free energy density. So I'll call that little f, the free energy density. So that's the total free energy per volume of the system. Okay, so if it's going to be a power series in Q for small q, let's start by just writing down what kinds of terms might go there. Well, first of all, there could be something which is 0th order in Q, that is independent of Q. Well, that's just some F0, okay? So I'll call that 0th order. Okay, how about first order? what can we write down that is first order, that is linear in the Q tensor? Well, what could we say, right? We want something that is linear in the Q tensor. So I'll write some guesses down here in red, okay? Could I just say something proportional to QXX? Well, that's not right because it treats the X direction differently than it treats the Y direction and the Z direction, okay? So let's use tensor notation to protect us from making a mistake like that, okay? That will involve that will respect the right symmetries. Okay, so could there be just something like Q alpha beta, right? A constant times Q alpha beta. Well, that's not right either because Q alpha beta is a tensor. It has two indices, alpha and beta. By comparison, the free energy density is a scalar. How can we make a scalar from a tensor, right? Well, if we had some vector lying around, some vector h, we could say, let's contract it with h alpha, h beta. That would make a scalar. But the thing is, we don't have a vector lying around so that we can make a contraction. There's no special direction other than the special direction that's built into the Q tensor itself. So that won't work either. What else could we do? Well, we could contract the two indices with each other to say Q alpha alpha, right? The good news about doing that is that, yes, it has all the right symmetries. It is a scalar, right? And it is totally allowed in the free energy. The bad news is it's zero, because this is, as we talked about a little while ago, this is the trace of Q, and Q has trace equal to zero. So there just isn't anything that can go there. There's no first order term. So let's move on and think about, well, can there be a second order term? For a second order term, that is something which has two powers of Q. Can we make a scalar out of two powers of Q? In fact, we can, right? And so one way we can do that, well, no, the way we can do that is to say Q alpha beta contracted with Q alpha beta. Right? When we have a term like this one, this is a scalar, right? Because it is contracted over the index alpha. It is contracted over the index beta. It has no free indices. This term could also be written in a few other equivalent ways, right? So because Q is a symmetric tensor, we could also write it like that, right? And this is equivalent to the trace of Q squared. So yes, so a term like this is definitely allowed in the Landau de Gennes free energy. So we could say the Landau de Gennes free energy has a second order term that could be some coefficient, which we don't know, times Q alpha beta, Q alpha beta. Okay, so this is second order. What about third order? So you remember when we were doing the Ising problem, there was no third order term, right? We couldn't find any third order term that had the right symmetry. What about now with the Q tensor? Well, actually there is something. We could write a term like Q alpha beta, Q beta gamma, Q gamma alpha. Because we're dealing with a tensor like this, we could write a term like this one, which is making a scalar out of 3 powers of the Q tensor. And so this is allowed in the free energy expansion. It could occur with some coefficient to be determined. What about fourth order? Well, that'll work too. We could have something that looks like Q alpha beta, Q beta gamma, Q gamma delta, Q delta alpha. All right, let's contract it over everything. That makes a scalar out of 4 powers of Q. You could also make a scalar by doing Q alpha beta, and then squaring that, or equivalently writing Q gamma delta, Q gamma delta, like this. Okay, so this is a second way to make a fourth order term. And of course, there are higher order terms as always. So we have 0th order, second order, third order, and fourth order terms. So similar to the Ising model, but a little bit different because it's with tensors instead of just an M scalar or a vector. And it's now allowing a third order term that was forbidden before. Okay, so this is something which amazingly is enough to actually learn something about the isotropic pneumatic transition, as I will show you on Monday. Okay, so let's break for here, and I'll be glad to answer any questions, and I'll see you on Monday when we continue on with this calculation.